we're going to be looking at exothermic reactions in particularly to look at sketching a diagram and labelling the key points in it. And we're going to look at what happens if we change some of the conditions. And the conditions that I want to look at are a different initial temperature, what happens when I change the initial temperature, higher or lower, and what happens if, sorry, you'll see why I'm going to use colours in a moment, what happens if I use a catalyst. But before I get into those, let's just go through the basics. So in blue, I'm just going to go through the general shape. In an exothermic reaction, we're told that heat energy is released. Exo out, thermic heat. All right. Enthalpy, in a nutshell, is basically all of the energy in a substance. So it's its kinetic energy of its particles, the bond energy between the particles, and the bond energy between the atoms. That's basically what we're looking at. The net of all of those energies is what we call enthalpy. If you want to go into real depth, I would strongly recommend looking at the enthalpy video at Khan Academy, but it is really, really beyond. It's basically telling you that the heat of a system, so long as we keep pressure the same, which we're assuming here, the heat of a system is the same as its enthalpy. All right. Of course, if pressure changes, that will change as well. As I say, Khan Academy if you want to look at something in a lot more depth than this. Okay, so if we're going to have heat energy released, that means the enthalpy must be decreasing. So the enthalpy change must be negative. That means we better not start our diagram down here because there's nowhere really to go. So let's start it nice and high. We're going to start with an energy level here, and this is our reactants. We're going to end up lower than that. Let's say, for argument's sake, down here. And after a reaction, we call those things products. We still use these terms even if it's only a physical change. For example, going from steam to liquid water, or from water to ice. We still use these terms in this type of diagram. It's just easier. It's a convention, as it were. However, most of us know that if we put reactants together, not a lot happens. If I was to put oxygen and hydrogen together in a balloon and just watch it, I'll be watching for a long time and being pretty bored. But if I do that and put a flame near it, it's a lot more exciting. I get a very loud bang and a very big burst of, actually it's sort of a pinkish colour flame, but it's so fast you don't really notice. And that's from the combustion of hydrogen. Okay, so what I've done is I've provided a flame, which is just a little bit of energy. And that's what we call the activation energy. So there must be a value somewhere above the reactants that is my activation energy. A value where if I have that much energy with those reactants, they'll actually do something. They will react. And that's quite right. So what I am going to do is, it doesn't happen spontaneously. Some react, then more react, and so on until they all have suddenly reacted. So you get this sort of shape. And it's very dramatic. I'm sorry, I'm going to need to tidy up the bottom there, but that's okay. And so I've got my activation energy has been reached, so a reaction will occur, making these products, and suddenly the enthalpy, so the energy of those substances, so the species as it were, is lower than what it was as a reactant. And what has been emitted out here has been heat energy. So that's the energy that you would feel. It feels hot. Okay. Right. So we've got our activation energy. That's done. We've shown exothermic because we've gone from reactants at a higher enthalpy than the products. Good. What we haven't got yet is our enthalpy change given. Now, the activation energy has nothing to do with it. Not the enthalpy change. What it has to do with is the difference between the enthalpy of the reactants and the products. So what I'm going to do is a dotted line back here, and then, sorry, it's not particularly straight up and down, read that. my enthalpy changes there. The arrow's going downwards because it's a negative change. That's what an exothermic reaction is, a negative enthalpy change. So the arrow goes down. In endothermic, the arrow would go up because we'd start somewhere down here and go up to here. So it'd be positive. And by the way, to do that, it must absorb energy. And normally that energy is heat, so such things would feel cold. Okay, so we've got a good understanding of the key parts of this diagram. We need to be able to reproduce this just to get to achieved. Just to label this, draw it and label it as an achieved criteria. We have to be able to do it for exothermic and endothermic. However, to show what's happening if we change some conditions, that's getting to a level of understanding to get us merits. So, I'm going to look at an initial different, start again. I'm going to look at a different initial temperature. So let's say that it was hotter to start with. What would that do to the enthalpy of the reactants? If it was hotter to start with, what would that do? Give you a hint to the kinetic energy of the particles. They're going faster. So the higher kinetic energy, you're going to have a higher enthalpy. All right? The bonds are probably going to be stretching a little bit more too, so there's a bit more happening there. So you've got more enthalpy if you start at a higher temperature. So if we're going to start at a higher enthalpy, then our start point's going to be, let's say for argument's sake, here. We also know that when we add heat, what normally happens to the rate of reaction? Well done. Okay, so if it's going to increase the rate of reaction, and we assume this is proportional to time, down the bottom here, then what's it going to get? What's going to happen? How can we show, that's a good way to put it, how can we show that this reaction happens faster? How can we show it on our graph? Let's say this is proportional to time. Cool, so I'm going to move this one over here. Okay, so I'm starting at a higher point. I'm going to move this one over a little bit. Great idea. So my reaction bit, this bit here, is going to happen a bit earlier. All right. Now, however much I've moved this up by, I have to do the same to the products as well. Because if I start at a higher temperature, I'm going to end at a higher temperature as well. There's only a certain amount of enthalpy that will be released as heat energy. So it means that at the end, it's going to be hotter than in my control. My blue line's my control. So I've got to measure that, and as I was told before, move it left a little bit. So I'm going to put my products line here. Keeps going to the end because they're made, nothing more is going to happen. So I'm now going to have my reactants and my products. Here's the bit that can really trip you. Do you think the EA changes or stays the same? Stays the same. It's an absolute value. If I give this much energy, it will react. By the way, that's why the reaction occurs sooner. Less energy has to be put in to reach activation energy. So you'll notice that the enthalpy change is the same, okay, if we've done it correctly. Okay, this and this should be the same. So delta H stays the same. It's our first really important part. Our EA stays the same. What has changed? Just, if we look at the products, one thing has changed. Their actual enthalpy value is higher because it's been done at a different temperature. Now I must stress this is only true if we keep the pressure the same. If the pressure changes, the graph's a bit different. But at level 2 chemistry, you can assume that pressure is uniform. So keep the same. Okay. So that's a catalyst. Delta H the same. EA the same. Awesome. But the actual enthalpies have changed and the rate of reaction should be higher. Okay. More successful collisions, that sort of thing. Okay, we're going to go for red for catalyst. Now let's go back to our control. So that's our enthalpy of our things. A catalyst works by bringing the reactants together in an orientation that allows them to react more readily. So they're more likely to react successfully or collide successfully. That's how a catalyst works, whether it's a transition metal or an enzyme or whatever. It brings those reactants together so that they can, in a way that they will have a higher probability, that's a better way, have a higher probability of reacting successfully or colliding successfully to react. Okay? So what it means is that more particles are going to have enough energy to react much, much quicker. And because more particles have got the, let's call it activation energy, have got the activation energy, then the whole substance, the beaker of water or whatever, doesn't need as much energy, activation energy, for this reaction to occur. So the net result is that EA decreases. The reaction often happens earlier because that's what catalysts do. They speed it up by reducing the amount of EA or activation energy that's required. So as I say, we're going to stick with our control line, and I'm only going to do the red where it deviates from the blue line. So we end up with a new EA I'm sorry, it's getting a bit messy now, so I'll just do it over this side instead. Oops. Again, we need to look at the similarities and differences. Similarity, the same enthalpy change, does nothing to that. A catalyst does not actually get involved in the reaction, so it doesn't affect the enthalpy of reactants or products. It does, however, change the activation energy by offering an alternate, better, pathway for the reaction. Okay? You need to be able to sketch, basically a control as it were, and then one of those two, and explain it in words. So that's what we're trying to look at today. Can you explain what's happening in these in sentences?